should be G. So that's what you are getting from the equation itself. Okay. So you do step-by-step solution. Y1 equals Y0 plus HG T0 Y0, Y2 is Y1 plus HG T1 Y1, Yn plus 1 equals Yn plus HG T Yn. Okay. So the idea is you start from some time t0, then t1, t2. This is tn. T3, and each interval is equally spaced. So you increase time by h, and suppose you start from here, y0, then you calculate y1, then you calculate y2, like this. I'm showing that they are increasing. It doesn't have to be that way. It depends on the solution. It could potentially decrease. It could oscillate. Anything can happen. But the thing is, you have different time points, and you start with initial y0, and you go one jump in time, calculate your y value. Jump in time, calculate your y value. So that's the idea. So what you are going to get at the end is a table time, t0, t1, t2, like this, and then your y value, y0, y1, y2, like that. So first question to you, what's the difference from this approach to an analytical solution approach? Like how they are very different from each other? Or what is the advantage of one over the other? Like if you compare, suppose you are given a differential equation, like if you know this numerical solution technique and you can write a code in MATLAB, and MATLAB has already written one for you, so you could simply plug in your differential equation and get the solution. So why do you care about learning all these analytical techniques? Or if you don't like MATLAB and hate computer, you can think, oh, like, why not solve everything in terms of sines and cosines? Why do you bother to do this kind of numerical solution?
That's not exact.
Okay.
But it's good for solving things that we don't.
That's right. So as I was giving you this receptor ligand example, which you cannot solve using analytical techniques, of course, this is the only way you can solve this. So that's very good. But now there are equations which you can solve with analytically, which you might want also to do. Like my question is then, why not just learn numerical technique? What's the advantage of analytical? Like, why do you care for an analytical solution then? There are some advantages.
Sometimes the analytical method is much faster.
It could be, but with today's computer, probably that's equivalent. Like you can solve the same thing as fast as like you can do analytically. But that could be one case, one reason. There are other. So suppose you are given an analytical solution for cell. Suppose you have analytical expression of number of cells growing in a system NT. Suppose someone tells you that you have this kind of exponential t plus C2 T. Suppose someone tells you that cell growth in a simple cultured dish follows this simple solution. Okay? Suppose it has some equation, but you get this solution. So what is the advantage of having this solution? That one advantage is you can easily calculate all sorts of derivatives, dn dt, d2n dt. So you know how, what is the, if you have analytical solution, you know its derivative, you know its second derivative, okay, exactly. So that's the advantage, like you know the behavior of this function, you know how exponential behaves, you know how t function behaves, or you know, say, sine and cosine behaves. So you know the behavior of those functions, whereas here you are getting bunch of time points and bunch of numbers. So now this is a discrete time interval. So you don't know in between whether the function oscillates 2 times or it increases rapidly and came back, or it did something different, like this behavior, this behavior, this behavior. This you missed between 2 time intervals, okay? Because you don't know the exact form of the solution. In between, you are guessing the solution. You are joining them by a kind of best fit curve, but you are not sure that what the real solution is. Okay. Whereas if you do analytical solution, you want to know at t equals t. That's the exact value of your solution at t equals t. Okay. There is no error. Okay. So one major advantage is in analytical solution, any time point you choose, you know the exact number for that time point. Whereas in numerical solution, if you choose something in between these time intervals, you have some sort of error or uncertainty. Okay? And that, of course, you can make up by decreasing the time step. But if you decrease the time step, your computational time increases. Okay? So that's the problem. And another problem is, if you know the functional form, you can calculate the derivative, second derivative, so you know the rate of change of cell growth or the acceleration of the cell growth. Those things you know exactly as well. Whereas here, if you just got the solution, and you are joining by the best fit curve, but if I ask you, what's the rate of change of this function? How do you do that? Of course, you can calculate discrete derivatives, but that's not as nice as calculating derivative of these analytical functions. Okay? So both approach has their own advantages. Analytical approach, if you can, then you can get, it's more exact, it's exact, you can calculate different things, and you also, it's easy to see the limits. So suppose you get this solution, and I ask you what happens if you go to t goes to infinity. Suppose you get this exponential solution, and I ask you what happens when time goes to infinity. 0. This is an analytical solution. You know how this exponential function behaves. Here, you cannot solve anything numerically up to infinity. You can solve up to, say, t some n, say 100 minutes, 1,000 minutes, 10,000 minutes, but there is a limit. So if it increases exponentially, you can say, okay, it's exponentially increasing, so we are guessing that it's going to increase like this. But that's your assumption, okay? So you have some idea by looking at the equation itself, but still, there is some amount of uncertainty there. But whereas if you have an analytical solution, just look at it, you know how exponential functions behave, and you can readily tell what's going to happen for t goes to infinity. So the limits long time limits and those kind of things are easier to get in analytical solution. So analytical solution definitely has its advantage, but the problem is in biology and in biomedical engineering, biomedical applications, often the problems are so complex that you don't have much hope of doing analytical solution in many cases. There are a few cases and you can do approximations, but in many cases you can't do analytical solution. And that is clear from receptor ligand binding. A simple equation like this doesn't have analytical solution. So you can imagine there are a lot more complicated situations than this, and you don't have hope for analytical solution. So you need to go through this numerical solution. So let me take a break for 10 minutes, and then I will show you one specific example of this. Solution is nt equals exponential time. Okay. Now, if you want to do Euler, let me write the equation here. dn dt. And suppose you want to solve it through Euler scheme, and I give you y's or n0 equals, say, 1. So n of 1. So this is the time index. Okay. So the idea is you have a bunch of time points, t0, t1, t2, and n0, n1, n2, like this. So that's what you are after. N1 is going to be N0 plus dn dt times h. If you look at the formula, dn dt, and what is dn dt in this case? That's n. So this I can write 1 plus nh. Now you do N2, you get N1 plus N times H. Now what is N1? N1 you already calculated to be 1 plus NH. So it's 1 plus NH plus NH equals 1 plus 2 NH. Now you go to the third step. dt, no, dn dt, this should be dn dt t equals 1 times h. That's n of 1 times h. So it's 1 plus nh plus n1 is 1 plus nh times h equals 1 plus 2 nh plus nh square. Did you follow? So for N2, I have N1, the same formula, and dn dt at t equals 1. So now my initial time point is 1 and final time point is 2. Okay? So I have 1 plus nh plus n1 times h.